Okay, so let's start with quantum statistics. Do you have any questions before we pass on, by the way? Okay, so the first problem you face when you are dealing with quantum statistics is that there is no longer phase space. We cannot talk about the momentum and the coordinates of the particles. So if you remember our statistical mechanics description was mainly based on rho, the density of states in the phase space. And so we first showed that the rho satisfies the Liouville theorem, and hence it has to be a function of the Hamiltonian or the number of particles, etc. And so the rest just basically follow. But if you cannot talk about phase space, you cannot talk about Liouville's equation, you cannot talk about rho. So that is one problem we have to resolve. And, well, basically that's the problem we have to resolve. Now, of course, in quantum mechanics, again, we will be dealing with our ensemble. We have our ensemble, but we cannot represent our ensemble as just points in our phase space. Now, in this ensemble, there are the states. You see, each member of our ensemble will basically be in some state. Let's say psi A. And when we have some observable, well, there is the expectation value of this observable in one of the states. You see, quantum mechanics doesn't really tell us that the observable should have a specific value, but for a given state, we can talk about the expectation value of that state, of the observable in that state. But then we have to sum over all the members of the ensemble, divide by the number of the members of the ensemble. This is, let's say, the thermodynamic, the ensemble average of this operator O. So we are basically, compared to the classical ensemble theory, here we are doing two averages, one with respect to the quantum mechanical state, and one with respect to the ensemble at the same time. Now, of course, this we can write in a slightly different form. Sum over all possible states psi A multiplied by the number of systems in my system that have this state psi A divided by the total number, then the quantum mechanical average. Well, you see, this is nothing but the probability of the state A. Well, you see, this is quite similar to the classical average. Similar in the sense that, okay, we have this, instead of the value of the operator in the microstate, we are talking about the quantum mechanical expectation value of that microstate, multiplying it with the probability of that microstate, and we are summing over all the possible microstates of my system. Well, let me take one more step from here. Insert some identity. I just inserted the resolution of identity in terms of a complete basis eigenstates of some arbitrary Hermitian operator. And for the time being, the n states are arbitrary. The only restriction I have is that they are orthonormal and complete. You see, these microstates psi A's, they need not even be orthogonal. They can be any microstate with some definite probabilities. Well, let me just rewrite it slightly. This is n N O sum over psi A Psi A N. I just rearrange the terms. You see, here I have psi A N. It's this term over here. Here I have the matrix element of O with between N and psi A. That is over here. I just changed their order. I did the summation over N for N psi A first, then the N first. I just changed the order of the summation also. Well, you see, this term over here doesn't really depend on the states N, it depends on my ensemble only. That is what I call rho. That's called the density matrix. And so in terms of this rho, the density matrix, I can write my average as N O times rho N. But you see, this is nothing but O times rho is an operator. It is an N element of that operator. And this is the diagonal element. When I sum the diagonal elements, O is just trace of O times rho. So basically, in this case, the density matrix contains all the information about my ensemble. You see, in the case of in classical statistics, we had defined, we gave it the same name, rho. It was the density of my states in the phase space. That's the probability distribution of in my ensemble in phase space. Here I have the density matrix. It's an operator. And this operator contains all the information about my system. And rho, if you remember, we had just wrote it as probability of A psi A psi A. Now the wave functions, if you are working, let's say, in the Schrödinger picture, they will be changing in time. So psi A's, they are changing in time. So we can look at how this density matrix changes in time. Well, rho dot will be equal to, you see, I have my microstates, my copies of my system in my ensemble. I look at each one and I determine what are their microstates. So I can basically determine the probability of a given microstate in principle. But once I determine their microstates, these microstates need not be stationary states. They can be any state. And so they will be evolving in time. Well, each one of them will be evolving in the same manner. So the PAs will not change. PAs will be time independent. But each microstate will be evolving in time. So when I'm taking this time derivative, I only need to take the time derivative of psi a's. So this is PA. Psi a dot, or let me write the time derivative explicitly. Psi a plus psi a p by dt psi a. So rho dot is equal to PA. What is the derivative of this ket?
From Schrödinger?
Sure. The ket browser and ket satisfy the Schrödinger equation. So what's that derivative? h bar or minus I over h. Well, let me just multiply with I h bar.
It's minus. It's minus.
Okay, so I multiply the left hand side by I h bar. So this is h psi a plus psi a. What is this? It is psi a, but the minus h. Minus because of that I over there. And I already used the fact that h is Hermitian. So that there actually we have h dagger. Well, this is nice. I h bar in the Schrödinger picture, keep in mind. This is equal to h times pa psi a minus pa psi a times h. Well, you see these parentheses, they are nothing but my density matrix. So this I h bar rho dot is h rho minus rho h. So it's the commutator of h and rho. Well, in equilibrium, we expect rho dot to be 0. And you see, this is quite general. Whatever your system is, I h bar rho dot corresponding to your system should be given by the commutator of h and rho. Yes, I'm just repeating that this is the Schrödinger picture. It's an operator that changes in time in the Schrödinger picture. So this should be equal to 0 in equilibrium. Well, basically we are back to what we had done in the classical system, in a sense. In the sense that, well, we can start with the canonical ensemble, microcanonical. Well, you see, the fact that it commutes with h also tells me that in a basis in which I write, in which the Hamiltonian is diagonal, I can choose it such that rho is also diagonal. Okay, so let me, before going there. Let's see. Because h and rho commutes, I can diagonalize them simultaneously. Well, it basically tells me that the matrix elements of rho in this energy basis should be some number times the Kronecker delta nm. Now we can go to the microcanonical. Well, in the microcanonical, we have a given energy. Then these probabilities, rho n's, will be basically 1 over gamma if En is equal to E and 0 otherwise. And then all the rest basically follows. In the canonical, rho n would be just e to power minus beta en divided by sum over n e to power minus beta en. Well, let's see. How else can I write this in the canonical ensemble? You see, rho in this basis is rho n and n, which is equal to e to power minus beta en and n. Of course, sum over n. Which divided by q, let's say. This is equal to sum over n, 1 over q, e to power minus beta h and n, because h acting on the nth state just gives me en. But now this operator over here is independent of n. But this operator over here is nothing but 1, identity operator. So basically this tells me that rho is equal to e to power minus beta h over q. Q was defined as the sum over e to power minus beta en, sum over all n. Well, I can write this as, just insert this 1. My states are orthonormal. That's what I will be assuming. But this is nothing but the trace of e to power minus beta en and n. Now I just converted that to an operator and took the trace. Do you see how I got there? From the first line to the second line? Well, I can basically do the same trick over there. Trace of, and this q is trace of e to power minus beta h. Well, all the rest will basically follow from what we had done before. Well, the nice thing about this trace expression is the partition function is just a trace of that operator. And the expectation value of any observable is just a trace of rho times O, that operator. Here this H is the Hamiltonian operator. So the nice thing is you don't have to use the energy basis for calculating these traces. And finally we have the grand canonical ensemble. And in the grand canonical ensemble, rho n is just e to power minus beta en minus mu n. N being the number of particles in that state, E being the number of the energy of that microstate divided by the grand canonical partition function. Just do the same tricks, and rho is actually e to power minus beta h minus mu n operator divided by the trace of e to power minus beta h minus mu n. This is the normalization. You agree? There is one question though. slight a point that you have to pay attention to. You see, what we had shown before is that H and rho should commute. Well, if you look at in the ground canonical partition function, H and rho commutes only if beta mu n and H commutes. Well, beta is a non-zero constant. So this is, beta is definitely non-zero, so I can just cancel that. So this means that mu times n and H commutator should be 0. Well, this basically implies that mu can be non-zero only if this commutator is 0. That is, the number of particles is conserved. Only if the number of particles is conserved, mu can be non-zero. Well, that kind of makes sense. If you remember why we introduced mu to start with, we said that the average number of particles should be fixed. But if the number of particles is not conserved in a given system, then you don't need to have an average number of particles. If you change your system, the number of particles can change. Well, this is true, for example, for the photon, for an electromagnetic radiation. Number of photons is not conserved. So basically it tells me that the mu for photons has to be 0, whatever your system is. So this will be important when we study blackbody radiation. Blackbody radiation is a gas of photons. Any questions up to here? So basically, well, this is all we need to do to keep in mind when we are doing quantum mechanics, quantum mechanical statistics. So most of the machinery that we had devised, we had used before, it's still valid. We can still use them. Just a couple of minor issues that we need to pay attention to. Also conceptually, this is the machinery that we are using. We are not looking at the phase space. We are not really using the P and Q space, but nevertheless we can talk about the density matrix, and we can use, for the density matrix, we can use exactly the same expressions that we had used before, as long as we keep in mind that we are using an energy basis to describe my microstates. Of course, rho need not be diagonal. This tells me that, here, I know that rho is diagonal in the energy basis, but it need not be diagonal in an arbitrary basis. So you need to pay attention to the off-diagonal elements if you are using some non-energy basis. Any questions? Let's do some simple applications. The Fermi and Fermi-Dirac. And Bose-Einstein statistics. Well, let me consider my system. Whenever we are talking about systems, we are always drawing these rectangular shapes, but they don't have to be rectangular. It's just general treatment. Let us pick one well, for simplicity, I will first assume that I can ignore to some extent the interaction between particles. So I'm ignoring the interactions which I'm assuming that they can be added kind of perturbatively or on an average basis. They can be, we can treat them on an average. And then let's say that we have a single particle can be in a given single particle state. So I just pick up a single particle state. Then I define my system. Let me just show that single particle state by A, and its energy is epsilon A, or psi A epsilon A. Well, my system is all the particles in the single particle state psi. Well, the number is not fixed. I mean, the particles, okay, we said that they are not interacting, but basically we are ignoring the interaction. We are saying that they modify the properties of the system very slightly. So there can be some interaction, and due to these interactions, the particle which started in the state psi A, it can go to some other state, and particles in other states can go into the state psi A. So this is my macro state, my single particle state. Now let's calculate the partition function, grand canonical partition function. It's the sum over all possible states of my system, e to power minus beta EA minus mu and A. Well, what is the energy of my system? If I have Na particles in my system, each one has an energy epsilon A, so this is the total energy of my system. And the microstates of my system are uniquely determined by the number of particles in my system. So these NAs determine my microstates. So Q is sum over Na of e to power minus beta epsilon A minus mu to the power Na. Now the next question is, what are the possible values of Na? How many particles are there? How many particles can there be in my microstate, in my single particle state? Well, for fermions, Na is equal to 0 or 1. Two fermions cannot be in the same state. For bosons, well, there are practically no restrictions. So Na can be 0, 1, 2, up to infinity. So Qa, my grand partition function, is equal to 1 plus e to power minus beta epsilon A minus mu for fermions. This is the Na is equal to 0 term, this is the Na is equal to 1 term. Well, for bosons, it's a geometric series, so it's just 1 over 1 minus e to power minus beta epsilon A minus mu for bosons. No, not QA, sorry. Well, I can write both of them in using a slightly shorthand notation. Let me write it as 1 plus eta e to power minus beta epsilon A minus mu to the power eta. And where this constant eta is 1 for fermions, minus 1 for bosons. So what's the number of particles on the average in my system? The average number of particles. Well, if you remember, or if you just let's look back, I want to bring a factor Na to the front, so I need to take the derivative with respect to mu. And if I take the derivative with respect to mu, there is an additional factor beta. So I need to take the derivative with respect to mu and divide by beta and divide by q. So this is 1 over beta 1 over q times the derivative with respect to mu of q, or 1 over beta k times t derivative with respect to mu of logarithm of q at constant temperature, or beta. This is equal to kt, derivative with respect to mu of logarithm of, well, q is 1 plus eta e to power minus beta epsilon minus mu times eta, because you see eta is in the as a power. Well, this is kt times eta. If I take the derivative with respect to mu, I get, well, the beta times e to the power minus beta epsilon minus mu times eta divided by 1 plus eta e to the power minus beta epsilon minus mu. Well, eta is either plus or minus 1, its square is always 1. Beta is 1 over kt. So the average number of particles in a given microstate, in a given single particle state, let's put the index E over there. This is, by the way, epsilon A. This is just equal to 1 over e to the power beta epsilon A minus mu plus eta. So if you just remember what the eta was, eta A for Fermi-Dirac, for fermions eta was 1. This is equal to 1 over e to the power beta epsilon A minus mu plus 1. Well, this is always less than 1, or let's say less than or equal to 1. In a certain limit, it will become 1. Well, this is kind of expected because there's either 0 particles or 1 particle. Their average can go from 0 to 1 and cannot go above 1. And now we have the Bose-Einstein statistics for bosons. This is 1 over e to the power beta epsilon A minus mu minus 1. This can be anything. It can be 0, it can be infinity, etc. But keep in mind that the total number of particles in my system should be equal to sum over Na No, it's not sum over Na, sum over psi A, all the one particle states of Na. But this tells me that if we are talking about bosons, let's define the ground state energy. To be zero. Well, it's just a shift in the energy. So N, there should be sum over all the single particle states of 1 over e to power beta epsilon A minus mu minus 1. Well, in fact, just look at over here. I mean, even here we could say something. You see, the average number of particles, it has to be larger than 0. It cannot be negative. But you see, if epsilon A is less than mu, here, in this Bose-Einstein statistics, if epsilon A is less than mu, then epsilon A minus mu is a negative number. Beta, assuming positive, and we had already discussed that in general it will be positive. This is a negative number. E to the power a negative number is less than 1. So this average just becomes negative average number. That's not possible. So that tells me that mu has to be less than or equal to 0 for bosons. For fermions, there is no such restriction. Well, you see, this sometimes gets confusing for any particle. And if you say that chemical potential is negative, remember how we define the chemical potential. Mu is basically the increase in the energy of your system if you add one more particle to your system, keeping the entropy and the volume constant. So you are adding a particle, it will have its own energy. And why is it negative? What does it mean to have a negative chemical potential? For fermions, it's positive. That's kind of expected, because what you usually do is, if you try to add them one by one, it's positive at least at low temperatures. You see, at the low temperatures, all the low energy states are already occupied. So if you want to add one more particle to your system, it has to go to the available energy level, which will be high. Now, the detail over here that you shouldn't miss is that the chemical potential is the change in the energy when you add one particle, keeping the entropy fixed. You see, if you increase the number of particles in your system, the entropy of your system will increase in general, because there will be more ways of distributing the energy among a larger number of particles. So entropy will increase in general, unless you decrease the entropy by changing some other parameter of your system. And that is the energy of your system. So if you add one more particle to your system, since the energy can be distributed in more ways now, you have to lower the energy in order to keep the entropy fixed. Now, this also happens for fermions at high temperatures, but at low temperatures, there's already some states, low energy states are occupied, they are filled, there is no possible different ways of distributing them. So even if you add one more particle, the entropy does not increase. So energy still increases at low temperatures. So any questions on these? So we have the Fermi-Dirac, the Bose-Einstein. This equation basically fixes what mu should be. And by the way, when we were discussing, for example, when we were treating identical particles, now there was a problem of exchange of identical particles. Well, if you exchange identical particles, does it give you a new, are you counting that as a new state or not? In the classical description, we were counting them as new states, just exchanging two particles. So what we did was we just divided them by n factorial, the number of ways that we can exchange them. But there was still a problem in this prescription that if two particles are in the same state, they are not really counted as new states. So it's exactly the same. We shouldn't even count them as new states. So the classical prescription of dividing by n factorial for identical particles didn't work if there are more than one particles on the average having exactly the same single particle state. But in this prescription, we are already taking that into account. So it's already over there. So kind of we resolve that problem exactly. Problem of identical particles. So although we didn't actually do much, since that the property of identical particles is already taken into account here, there is no Gibbs paradox. That's in the entropy of mixing, etc. Questions? So let's finish here today. And then we will continue next week. Remember, on Thursday we have midterm. Okay, so see you.